continue our discussion on KVL, KCL and power balance taken from the last lecture. So, we considered this simple circuit. With respect to this simple circuit only, I will build up the thing, so that you understand. So, our circuit was, I will redraw here, it is 30 volt, there was a source. With the help of this simple circuit, I try to highlight many of the interesting things here. So, this was our simple circuit. We considered 0.4 ohm, na? 0.6 ohm, and this was 4 ohm, 4 and that is 6. This was 4 ohm and that is 6 ohm. And we found out various currents in the circuit. It was 6 ampere after solving the circuit from our school days knowledge, series parallel thing, and this was 4 ohm, 4 ampere and this was 10 ampere. This circuit was solved, and we then immediately can identify which of these fellows is delivering power. This 30 volt source must be delivering power, because through the plus 10 ampere is coming out. Voltage drop here is of this polarity, therefore, it is absorbing power. Similarly, voltage drop here will be of this polarity, it is absorbing power, it is absorbing power, and 300 watt was balanced. I will now tell you another important thing. We say that potential difference exists between 2 points. For example, I say that this point, let me call this is O, and this point is say A. Okay. Now, the next question is, if I connect a voltmeter across AO between O and A, if I connect an ideal voltmeter, what will be its reading? How to find it out? And that voltage I will call it VAO, that is, I am interested to know potential of this point A with respect to O. So, this is the thing you should read, potential of A with respect to O I want to find out. What should I do? What you should do is this: you start your journey from the point O and try to reach point A, and when I say I want to reach point A, I have several options. I can go this way, I can go this way starting from O, and I can go this way. Whichever way, whichever path you choose, VAO will be an unique number. So, let us see, suppose you go by this way. So, I will write VAO. So, I will start my journey from O. From this I am going like this. So, from this to this there is no voltage drop, no resistance in this path. Then from this to this there is a voltage rise minus to plus. So, write plus 30 volt. Then from this to this, what is the voltage drop here? 6 volt, 10 into 0.6, and it is from plus to minus, and then minus 6 volt. So that this voltage will become equal to 24 volt. Therefore, potential difference, if you connect a voltmeter between these two, I will say VAO is 24. I expect that voltmeter to read 24 volt. As I told you, it does not matter how you reach point A starting from O. For example, if you go via this path, then from here to here there is no voltage drop, but from here to here the voltage drop is this plus minus 6 ampere 4. So, 24 volt. So, you have reached this point, then from this to this you have reached A. So, that is also 24 volt. Similarly, this is also via this path, from this to this no voltage drop, from this to this the voltage drop is plus minus 24 volt, because 4 into 6. So, 24 volt, and then from this to this no voltage drop. Therefore, you should understand it will be often necessary as we go further into other aspects of circuit analysis. It is often necessary to find out the voltage between any 2 points of a network. For example, if I consider a slightly complicated network like this is some resistance. Although I have not told anything about current source etc., but suppose there are circuits like this, and to highlight the point. Suppose a circuit exists like that, all the values are known, and as I told you, by applying simple KVL, KCL in closed loops and KCL at the junctions, you will be able to solve the circuit. That will be the main part of the course, that we will discuss. But what I am trying to tell, see, there are now several junctions existing here. For example, you say this point is A, this point is suppose O, this point is B, this point is C, this point is D, this point is suppose E. This O point is all O, this is also O, because no element exists here. What I am telling, if I ask you to calculate what is the voltage VDO, it has got a meaning. So, what I am telling, that to find out VDO, potential of D with respect to O, you start your journey from O and try to reach point D via any path you like. For example, in this case I will try to reach the point D via this path, O to C I will go, then C to D, and while going I will note down what is the voltage drop here, which I must know with polarity. Similarly, I must know the voltage drop here, then I will be voltage rise or voltage drop. If it is a voltage rise, plus sign, if it is voltage drop, there will be minus sign, you can reach D. And this result VDO will be unique for a given circuit with all the circuit elements and sources, known sources. Similarly, you could reach D via this path. You have to then take only one voltage drop. You could reach this circuit via this path, but VDO will remain same. From this to this voltage rise, perhaps depending upon current etc., I will mark the polarity of the voltage here, then take plus minus reach D. Similarly, I could reach the points in this path. Therefore, given a circuit, after you have solved the circuit, you know all the currents in the branch of the circuit. After knowing all the currents, you know the voltage drop existing across each elements, and then I told you that choose two junctions, 2 points in the circuits. You should be able to calculate the voltage existing between any 2 points in the circuit. For example, somebody may be interested to know VBO, then he should start his journey, try to reach P, and algebraically sum the voltage drop across the elements that he encounters along that particular path. He could choose this point and that point. Understood? So, this is how I can calculate the voltage between any 2 points in the circuit, and we shall use that knowledge often in circuit analysis. Essentially, it means that when you calculate VBO, whatever will be the number, if you connect a voltmeter between BO, that will be the reading of the voltmeter, ideal voltmeter. Clear? So, this is the idea of a voltage source. I mean, potential difference between any 2 points. Now, I will tell you something about the sources before I take up the circuit elements R, L and C separately. Okay. Sources. As I told you, sources may be voltage sources or it may be a current source. Current source is perhaps it is very we are not familiar with that. You go to the market, you can buy a battery which is nothing but voltage source, but go to a shop, ask for a current source, it is not there. That is the thing. Of course, in practical circuit you can develop a current source using electronic devices like current source inverter, those things are there. But in the market you will not be able to purchase a current source, but a battery you can always purchase. Voltage source we are used to, things started with voltage source. Okay, there was battery, then people started thinking it is only voltage source, generate voltage to get power. So, rotating machines, this, that, all these things are in general voltage sources. So, a voltage source could be a fixed voltage source, fixed, or it could be time varying. As I told you, a fixed voltage source, in general both the sources could be ideal and non-ideal. Acha, ideal fixed a practical voltage source. A practical DC voltage source. DC means constant voltage, like a battery. A practical means it will have some internal resistance R, and this is the EMF in the circuit, and these are the two terminals which is available. From the battery terminals you really do not have any access to this terminal. So, this is called internal resistance of the source. And across these two terminals you connect your load, say a light, is not load resistance, current will flow. But what happens is the voltage across these 2 points is not same as E, because we have just learned if it is A, if you call this point O with R and RL connected, this is I. What will be the voltage drop here? IR. So, what is VAO? VAO is the voltage which is appearing across your load resistance, for example, a lamp. How much is that voltage? From this to this I will start minus to plus, it is plus E. Then from this to this minus I r, and I will reach point O. So, depending upon the current, this voltage which is actually appearing across the load will be less than E, because and the remaining voltage will be dropped inside the battery, that is called internal drop. This is how we denote a voltage source. This is a practical voltage source. What is an ideal voltage source? Ideal voltage source, internal resistance is 0. That is, its representation will be just like that. And here if you connect a load resistance R L, then what is VAO? Potential of A with respect to O. VAO is the voltage which is coming across R L, is not? Current will flow. How much? It will be start from O, reach A, that is only E. There is no internal resistance like this. So, it will remain always E, no matter what is the value of I. You go on varying R L, voltage across the load will remain same, always constant. But here with internal resistance, there will be internal drop inside the battery, which is a function of current. Therefore, if you draw the characteristics of a ideal voltage source against current, when I is 0, when I is 0 means when this R L is disconnected. When I is 0, no R L is connected, that is suppose imagine there is a switch, it is open circuited. What will be with I equal to 0, this voltage will be equal to E, but with I increasing, that voltage will have a drop like this. So it is a function of current. Of course, the internal resistance of a practical source should be small, is not? Otherwise, all the powers inside the battery, there will be large power drop in the battery will become hot and so on. No one going to buy a battery with large internal resistance, one must see that. Okay. So, this will be the V I characteristics of a practical voltage source. Y is equal to y minus C x. So, minus m x plus c, slope of the line can be calculated. So, for any current I, a particular current I, who decides that current? If you change R L, I will change. Therefore, for this current, this is the total voltage and this much will be your I R. So, from E subtract I R, you get this is the voltage applied across R L. It simply tells that. What about an ideal voltage source? It will be like this. This axis is I and this axis is suppose voltage. No matter whatever is the current here, the voltage available across the load VAO is equal to E. It will be a flat line. Therefore, with no internal resistance, potential difference VAO remains constant all the time. However, it is not the case when there is internal resistance of the source present. So, this is the scenario at least with DC constant values, ideal battery representation and ideal voltage source, a practical voltage source representation. Now, I shall give you some idea about what a current source is. As I told you, we are not used to current source, and I simply told you it is represented like this. A current source may be a 2 ampere current source. For example, a battery, ideal battery may be written plus minus 5 volt. So, a current source with 2 terminals will be represented like this, symbolic representation. But where from it comes and why we, although we know no current source at least is not used very much by any common users, why do you study this and why at all, what is the implication of the current source and how it comes from. Acha, to explain that I will take this, you please follow me very carefully. Suppose you have a practical voltage source with internal resistance. This is a practical voltage source, or these are the 2 terminals of the battery. This terminal is never seen by us inside the battery. So, these are the 2 terminals available to me, and I told you this point is A, this point is O. What will be VAO when nothing is connected? No current is flowing, VAO start from O, from this to this E, no current, no voltage drop here, plus minus. If this is suppose like this, and therefore, with S opened, VAO is equal to E with S opened. Here is a switch which can be connected this side with S opened. But with S closed, sorry, this is what I discussed in just some time before. VAO will be with this switch closed here, there will be some current now I. The value of the current can be easily calculated if you know small r and RL, which is equal to E by R plus RL, and VAO will be nothing but E from this to this plus from this to this minus IR, and I value is this. So, that will be slightly less as I told you. So, I have to bring the idea of a current source, you can think in this way. Okay. In this circuit, because we are conversant with voltage source, I is equal to E divided by R plus RL, no doubt about it. V is equal to IR, that is the KVL, and I is voltage by resistance. Acha, now what I will do is this, I will do some mathematical operation on this particular expression. What I do, I divide numerator and denominator by this small r. That is, I will say that this is nothing but E by R and R plus RL by R. I can do that because R is not equal to 0, it is a practical voltage source. So, I can divide it. since R is not equal to 0, a practical battery. Acha. Now, this quantity E by R is the property of the source. It has nothing to do with R L. This E and this divided by small r, this quantity is decided by the source, by nobody else, and not your R L is going to change it. So, let this current E by R be called this current as ISC. What is physical meaning of this? This battery with this internal resistance will deliver a current if R L is made equal to 0, if these two terminals are short circuited, is not? Then only this ISC will flow if R L is equal to 0 here, E by smaller. So, this current is a fixed current and is decided by the battery parameters. No load is going to change this value. I am not short circuiting it, but I am telling if you short circuit the battery terminals, whatever current it will deliver, that current ISC. So, this can be written as ISC, this E by R is ISC into R by R plus R L, this will be the thing. Is it? This is my actual circuit I was doing, but somebody says okay, that is fine, you are satisfied with this one fine, but he thinks somewhat ahead, thinking that okay, this can also be written like this ISC by R plus R L. Acha. Now, this point you just try to listen carefully, the next course of argument. What I am telling is this: suppose you have two resistances, we have used this in the first lecture, this idea. Suppose this current is known I, then what will be the, this current is I and this current is I 1, this current is I 2. What will be the value of I 1? Suppose I is known, this will be equal to the total current coming across this parallel, coming to this parallel combination, this is also I, total current into the other resistance R 2 divided by R 1 plus R 2, is not? We know this parallel current divisions in two resistances in parallel. So, here also it looks like that okay, there is some fixed current ISC. Our problem is to find out the current flowing through R L in this circuit. We did it, E by small r plus R L, but I am also trying to interpret that result from some other point of view. That is okay, that is fine, you divide by small r, then you get this expression and you say that okay, then I think of this formula and say that okay, ISC is coming, then there are two resistances in parallel R into R L, and in this branch this current is ISC, is not? So, to find out the current flowing through R L in this circuit, somebody thinks somewhat differently. He says that okay, solving this circuit is same as, imagine you know E, You know internal resistance, E by R you calculate, and then connect R and RL in parallel, and you will get back this current I, because ISC into small r divided by sum of these two resistances gives you this current. See, always if you look at the things, always try to see, okay, this problem can be also imagined in this way. There is somebody sending a constant current ISC. This circuit can be also thought of without any loss of generality. That is another way of looking at this simple problem, is to say that look, there is a constant current here ISC, and there is your this internal resistance of the battery smaller and this capital RL, they are in parallel, and this I will denote it by a circle with an arrow. The arrow is decided by in which direction battery was sending current, because of that. Now, as I told you, up to this portion on the left of this red line is the source portion, because you see here small r is there, here is E by R is there. Therefore, I will say that if you have a circuit like this, a battery with internal resistance, mind you, R, this is A, this is suppose O, and here is your RL, this current is I, and this voltage is E. What are the things known? Battery, this EMF is known, internal resistance is known. What I am telling, okay, you live with it, you get everything correct, fine. But perhaps somebody thought it to look at it from different angle. He says that, oh, you are solving this circuit. Between A and O, he says, here is your RL, you are looking into this circuit, and you know it is a battery in series with resistance. He tells that look to the source side, what exists is this. That is all, and you will always get correct current across the load and correct voltage across VAO, no problem. See, looking at the same thing from different angles gives rise to the fact, although we do not know anything about current source, whether it can be manufactured or not at this stage at least, but somebody says look here, there was it was not a EMF and R in series, but it is there is a constant current existing in this path in parallel with this small r, that is what is present. That is, if this thing would have been in a black box, these two things are indistinguishable. Okay, this argument is as strong as this argument. He may say no, no, there was no battery in series with a resistance, here was a constant current ISC whose value is E by R in parallel with a resistance. Therefore, a current source I will denote it. We will be discussing about this more often than this simple example, but if you start from this, it will be easier. Therefore, I now say that this portion, only this portion excluding this R, is an ideal current source. I may say like this, of what magnitude? E by R. And a current source in parallel with the internal resistance R is a practical current source. So, please although very simple, but try to understand the nicety of looking at these same things in a different angle. Between point A and O, if you look into the circuit, I will say, who told you there is E and R in series? Are inside this black box, it is actually a current source which supplies constant current. I can interpret it in parallel with a small R resistance, and these are the two terminals AO of your that battery. And to the external world, to the right side of this blue line, whether you consider this to be present or this E and R in series to be present, it does not make a difference. That is what I am trying to tell. We will continue with this in the next class. Thank you.